Infinite series. Example. Consider the sequence n over 2 to the n as n goes from 1 to infinity. Let's first list the first several terms of this sequence. We have 1/2, 2/4, 3/8, 4/16, 5/32, 6/64, and so on. The 20th term is 20 divided by 2 to the 20th power. Now let's create a different but related sequence by keeping a running total of the terms of this sequence. We'll begin with 1/2, and then add 2/4, which gives us a total of 1, then add 3/8, which gives us 11/8, adding 4/16 gives us 26/16 or 13/8, adding 5/32 gives us 57/32, and so on. In fact, if we continue this until we've added up the first 20 terms, we'll have a sum that equals 1.99998 when rounded to 5 decimal places. So we've taken a sequence, which we'll refer to as a sequence of terms, and we've created a sequence of running totals, which we refer to as the corresponding sequence of partial sums. We can view the result of adding more and more terms as an infinite sum, which is called a series or infinite series. The sum of the series is defined by the limit of the partial sums. Here it appears that the sequence of partial sums is converging to 2, and if that's the case, the series is equal to 2. Let's also notice here that such a sum cannot be finite unless the sequence of terms approaches 0. In particular, if all the terms are positive and do not approach 0, then the partial sums simply get larger and larger, and that sequence will diverge to infinity. Definition. Given a sequence a sub k, k from 1 to infinity, the infinite series, the sum from k equals 1 to infinity of a sub k, which equals a1 plus a2 plus a3 and so on, is defined to be the limit of the sequence of partial sums s sub n, as n goes from 1 to infinity, where s sub n is the sum as k goes from 1 to n of ak, which is a1 plus a2 and so forth up to a sub n. That is, the sum from k equals 1 to infinity of a sub k is equal to the limit as n goes to infinity of the sum from k equals 1 to n of a sub k. When this limit exists, we say the series converges, otherwise it diverges. Example. Consider the series, the sum from k equals 1 to infinity of 1 over k times k plus 1. Listing out several terms, we see that this equals 1 over 1 times 2, plus 1 over 2 times 3, plus 1 over 3 times 4, plus 1 over 4 times 5, and so on, with the nth term being 1 over n times n plus 1. Now let's look at the sequence of partial sums. First term is 1/2. The second is 1/2 plus 1/6, or 2/3. The third term is 2/3 plus 1/12, which is 3/4. The fourth term is 3/4 plus 1/20, which is 4/5, and so on. Now in this case it's easy to see a pattern in the partial sums. It's clear that the nth partial sum is equal to n divided by n plus 1. So we have s sub n equal to n over n plus 1, and it's easy to see that that sequence converges to 1. Therefore, the sum from k equals 1 to infinity of 1 over k times k plus 1 is equal to 1. Now let's look at another approach to determining the value of the series. A partial fraction expansion on 1 over k times k plus 1 allows us to express this same series as the sum from k equals 1 to infinity of 1 over k minus 1 over k plus 1. Now with the kth term expressed this way, let's list out a few terms. The first one is 1 over 1 minus 1/2. The second term is 1/2 minus 1/3. The next term is 1/3 minus 1/4, and so on. And the nth term would be 1 over n minus 1 over n plus 1. Now notice that we have minus 1/2 plus 1/2, which equals 0, minus 1/3 plus 1/3, which equals 0. Then we have minus 1/4 plus 1/4, and so on, And if we continue this up to the term 1 over n minus 1 over n plus 1, everything will have been eliminated except the 1 in the first term and minus 1 over n plus 1. Therefore, the nth partial sum, S sub n, is equal to 1 minus 1 over n plus 1. This is equal to the same n over n plus 1 that we had before, and the limit of that is equal to 1 as n goes to infinity. A series whose nth partial sum can be determined this way is called a telescoping series. Example. Consider the sum from k equals 0 to infinity of 1 over 2 to the kth power, which equals 1 plus 1/2 plus 1/4 plus 1/8 plus 1/16 and so on, where the nth term is 1 over 2 to the n. Let's look at the sequence of partial sums. Those are 1 plus 1/2 or 3/2, 3/2 plus 1/4 equals 7/4, 7/4 plus 1/8 equals 15/8, then 31/16, 63/32, and so on. Here the denominators are just powers of 2, and each numerator is the next power of 2 minus 1. So the nth partial sum is 2 to the n plus 1 minus 1 divided by 2 to the n, which can be rewritten as 2 minus 1 over 2 to the n, making it clear that the limit as n goes to infinity of the nth partial sum is equal to 2. Therefore, the sum from k equals 0 to infinity of 1 over 2 to the k is equal to 2. Another example. Consider the sum from k equals 0 to infinity of minus 1 to the k over 2 to the k, which equals 1 minus 1/2 plus 1/4 minus 1/8 plus 1/16 minus 1/32, and so on, with the nth term being minus 1 to the n over 2 to the n. Notice that the terms here are the same as in the previous example, except with alternating signs. Such a series is called an alternating series. Let's look at the sequence of partial sums. We have 1 minus 1/2 equals 1/2, 1/2 plus 1/4 equals 3/4, 3/4 minus 1/8 equals 5/8, then we have 11/16, 21/32, and so on. Here it's not as easy to find a formula for the nth partial sum, and so we clearly need better ways of doing things. But notice that, starting with 1/2, if we multiply each numerator by 3, those numerators become 3, 9, 15, 33, 63, and so on. Each of those numbers differs from a power of 2 by either plus or minus 1. In fact, the numerator of the nth partial sum is equal to 1/3 of 2 to the n plus 1 plus minus 1 to the n. And so the nth partial sum is 2 to the n plus 1 plus minus 1 to the n divided by 3 times 2 to the nth power. We can rewrite that as 2/3 times 1 plus minus 1 to the n over 2 to the n, which makes it clear that the limit of the partial sums is 2/3. Therefore, the sum from k equals 0 to infinity of minus 1 to the k over 2 to the k is equal to 2/3. Geometric series. Given a real number x, the series, the sum from k equals 0 to infinity of x to the kth power, which equals 1 plus x squared plus x cubed, and so on, is called a geometric series. The sum of this series, as always, is the limit of partial sums. It's equal to the limit, as n goes to infinity, of 1 plus x squared, and so on, up to x to the n. We can get a closed formula for the nth partial sum as follows. Let's first write S sub n equal to 1 plus x squared, and so on, up to x to the n, and then notice that x times S sub n is equal to x plus x squared plus x cubed, and so forth, up to x to the n plus 1. Now let's subtract x times S sub n from S sub n. We have S sub n minus x times S sub n equal to 1 minus x to the n plus 1, because 1 and x to the n plus 1 are the only terms that are not shared by S sub n and x times S sub n. We can factor S sub n from the left-hand side here, writing it as 1 minus x times S sub n, so if we divide by 1 minus x, we have S sub n equal to 1 minus x to the n plus 1 divided by 1 minus x, provided that x is not equal to 1. If x is equal to 1, then the series is simply 1 plus 1 plus 1 plus 1 and so on, which is clearly divergent. So these are the partial sums of a geometric series if x is not equal to 1. S sub n equals 1 minus x to the n plus 1 divided by 1 minus x. Therefore, the limit as n goes to infinity of s sub n is equal to 1 minus the limit as n goes to infinity of x to the n plus 1, all divided by 1 minus x. Now, since we're already assuming that x is not equal to 1, the limit as n goes to infinity of x to the n plus 1 power exists only if x is strictly between minus 1 and 1, and in that case, that limit is 0. So the limit as n goes to infinity of s sub n is equal to 1 over 1 minus x, provided that x is strictly between minus 1 and 1. That is, the sum from k equals 0 to infinity of x to the kth power is equal to 1 over 1 minus x if the absolute value of x is less than 1, and the series diverges if the absolute value of x is greater than or equal to 1. Example: the sum from k equals 0 to infinity of 2 to the k divided by 3 to the k, which equals 1 plus 2/3 plus 4/9 plus 8/27 and so on, is equal to the sum from k equals 0 to infinity of 2/3 to the kth power. Therefore, our formula for the sum of a geometric series says that this equals 1 over 1 minus 2/3, or 1 over 1/3, which equals 3. Another example: the sum from k equals 0 to infinity of minus 1 to the k over 2 to the k, which equals 1 minus 1/2 plus 1/4 minus 1/8 and so on, is equal to the sum from k equals 0 to infinity of minus 1/2 raised to the kth power. Therefore, our formula for the sum of the geometric series says that this series is equal to 1 over 1 minus negative 1/2, or 1 over 3/2, which equals 2/3. A few remarks. The summation index is a dummy index, much like the integration variable in a definite integral. For instance, the sum from k equals 1 to infinity of k squared over 2 to the k is the same thing as the sum from I equals 1 to infinity of I squared over 2 to the I, which is the same as the sum from n equals 1 to infinity of n squared over 2 to the n, etc. The starting value of summation index needn't be 1 and may be chosen for convenience. For instance, each of the following is a description of the series 1 over 3 times 6 plus 1 over 4 times 7 plus 1 over 5 times 8 and so on. With a starting index of 1, we have the sum from I equals 1 to infinity of 1 over I plus 2 times I plus 5. With a starting index of 3, we have the sum from k equals 3 to infinity of 1 over k times k plus 3. And with a starting index of 6, we have the sum from n equals 6 to infinity of 1 over n minus 3 times n. Each of the following is a description of the series 2 over 3 cubed plus 3 over 4 cubed plus 4 over 5 cubed and so on. With a starting index of 2, the sum from k equals 2 to infinity of k over k plus 1 cubed. With a starting index of 3, the sum from k equals 3 to infinity of k minus 1 over k cubed. And with a starting index of 1, the sum from k equals 1 to infinity of k plus 1 over k plus 2 cubed. Arithmetic properties of series. If the sum from k equals 1 to infinity of a sub k converges, and c is a constant, then the sum from k equals 1 to infinity of c times a sub k converges, and the sum from k equals 1 to infinity of c times a sub k is equal to c times the sum from k equals 1 to infinity of a sub k. In other words, a factor that's common to all terms may be factored out of the series. This is the distributive property of multiplication over addition. If the sum from k equals 1 to infinity of a sub k and the sum from k equals 1 to infinity of b sub k both converge, then so do the sum from k equals 1 to infinity of a sub k plus b sub k and the sum from k equals 1 to infinity of a sub k minus b sub k, and the sum from k equals 1 to infinity of a sub k plus or minus b sub k is equal to the sum from k equals 1 to infinity of a sub k plus or minus the sum from k equals 1 to infinity of b sub k. In these two respects, convergent series behave just like finite sums. Example. Let's look at the sum from k equals 0 to infinity of 3 to the k plus 1 minus 2 to the k, all divided by 5 to the k. Writing out the first several terms, this is 2 plus 7 fifths plus 23 25ths plus 73 over 125, and so on. The quotient 3 to the k plus 1 minus 2 to the k over 5 to the k may be broken up into two terms as 3 to the k plus 1 over 5 to the k minus 2 to the k over 5 to the k. And so the series may be broken up into two terms as the sum from k equals 0 to infinity of 3 to the k plus 1 over 5 to the k minus the sum from k equals 0 to infinity of 2 to the k over 5 to the k. Now let's factor 3 from the first series here, and we have 3 times the sum from k equals 0 to infinity of 3 fifths to the k minus the sum from k equals 0 to infinity of 2 fifths to the k. Now we can apply our formula to each of these series and obtain 3 times 1 over 1 minus 3 fifths minus 1 over 1 minus 2 fifths. The first term is 3 times 5 halves, and the second term is minus 5 thirds, so we have 15 halves minus 5 thirds, which equals 35 over 6. Example. Find the sum from k equals 3 to infinity of 1 over 3 to the k, which equals 1 over 27 plus 1 over 81 plus 1 over 243, and so on. Notice that this would be just an ordinary geometric series if the sum started with k equal to 0. We'll use this example to illustrate 3 approaches for dealing with that issue. The first approach is to simply rewrite the sum from k equals 3 to infinity of 1 over 3 to the k as the sum from k equals 0 to infinity of 1 over 3 to the k minus the first 3 terms, 1 plus 1/3 plus 1/9. Now we apply the usual formula to the sum from k equals 0 to infinity of 1 over 3 to the k and get 1 over 1 minus 1/3, and then subtract 1 plus 1/3 plus 1/9, which equals 13/9. So we have 3 halves minus 13/9, which equals 27 over 18 minus 26 over 18 equals 1/18. Now let's take a slightly different approach. Let's write out the first few terms of the series. We have 1 over 27 plus 1 over 81 plus 1 over 243, and so on. And let's notice that 1 over 27 is a factor of all the terms here. In fact, we have 1 over 27 times 1 plus 1/3 plus 1/9, and so on. And that is nothing but 1 over 27 times the sum from k equals 0 to infinity of 1 over 3 to the k. And so we have 1 over 27 times 1 over 1 minus 1/3, which equals 1 over 27 times 3 halves, which is 1 over 18. Next, let's take the sum from k equals 3 to infinity of 1 over 3 to the k and change the index so that the index begins at 0. We'll replace k with 3 plus I. Then k equal to 3 corresponds to I equal to 0, and we can rewrite our series as the sum from I equals 0 to infinity of 1 over 3 to the 3 plus I power. Now there's really no need to use a different letter here for the index, so let's just write the sum from k equals 0 to infinity of 1 over 3 to the 3 plus k. This is an example of what's sometimes called index shifting. Now, since 3 to the 3 plus k is equal to 3 cubed times 3 to the k, or 27 times 3 to the k, we have a common factor of 1 over 27 times the sum from k equals 0 to infinity of 1 over 3 to the k. Now we can apply our formula for the sum of the geometric series and write our sum as 1 over 27 times 1 over 1 minus 1/3, which is once again 1 over 18. Notice that both the second and third approaches here amounted to essentially the same thing. Basic test for divergence. If the sequence of terms a sub k, as k goes from 1 to infinity, does not converge to 0, then the series, the sum from k equals 1 to infinity of a sub k, diverges. Warning: there are divergent series whose terms do converge to 0. For example, the sum from k equals 1 to infinity of 1 over k, which equals 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5 and so on, is called a harmonic series. To see why this series diverges, let's start by writing out the first 16 terms, 1 plus 1/2 plus 1/3 and so forth up to 1/16, and then group terms as indicated here. Notice that after the term 1/2, we group 2 terms, and then we group 4 terms, then 8 terms, and we continue that pattern, grouping terms in powers of 2. In other words, we would then group 16 terms, followed by 32 terms, followed by 64 terms, and so on. Now notice that 1/3 plus 1/4 is greater than 1/2, and 1/5 plus 1/6 plus 1/7 plus 1/8 is greater than 4 times 1/8, which is 1/2, and 1/9 plus 1/10 and so on up to 1/16 is greater than 8 times 1/16, or 1/2, and so on, and it turns out that all of our groupings represent numbers that are greater than 1/2. So this sum would be greater than 3/2 plus 1/2 plus 1/2 plus 1/2 and so forth, but that sum is not finite since its terms do not approach 0, and so the harmonic series must diverge. In fact, it turns out that the sum of the first 2 to the n terms here, for n greater than 1, is greater than 1 plus n over 2. Therefore, the sequence of partial sums diverges to infinity. Therefore, it makes sense to say that the sum from k equals 1 to infinity of 1 over k equals infinity. So the harmonic series provides us with a very important example of a divergent series whose terms approach 0. So while we can conclude that a series diverges if its terms do not converge to 0, we cannot conclude that a series converges simply because its terms do approach 0. In fact, the next topic that we will study is how to determine whether a series converges when its terms do approach 0.